So we'll continue looking here at a couple more trusses. So realize what you're asked to do here is solve for the internal forces in all of the members of this truss. So what makes it a truss? You see all the connections are pinned connections, right, up at D, B, A, and C. And all of the loads that you see are concentrated at the nodes. And not that those members don't have any self-weight, but it's substantially less than the magnitude of the point loads that are applied to the truss. So also all the members here are two-force members. Every member, like AD, is pinned at its end. Same with BD, same with CB and BA. So we see that we obviously have 5 members in this truss. We have an external pin and an external roller over there at C. And we're asked to solve for all of the internal forces. So we're going to go through and create all the different free body diagrams. So we can go ahead and start with the whole structure free body diagram. Over at A we have translational restraint. That's over F1, F2. We've got a translational restraint, which would be perpendicular to the ground, and I've called that F3. So we have 3 external unknowns, and so this would be externally determinate. We could solve for those 3 forces just by using statics and that single free body diagram. So we will eventually go do that, but right now what we're going to do is look at all the other free body diagrams that we could create. So we can take out our blue saw and we can go ahead and cut out joint D. And so when we do that, we end up exposing the internal force right there in AD, BD, and DC. And so there's our free body diagram that we would see from exposing or cutting out joint D. 3 internal forces in AD, BD, and CD. And so we'll get ready to do a couple more. We're going to take out that blue saw again. Going to go ahead and cut, ooh, that's a big blue saw. Go ahead and cut joint A away. And we'd end up with a picture that looks like that down there. So notice that we've got equal and opposite internal forces. I've drawn them both in tension. So they're both pulling away from the joint. So the member right here is in tension, just like that member is drawn in tension. So that internal force has a sense, not a direction. And so we can create 2 other joint free body diagrams. We can go ahead and cut out joint B right there. And we can also do the same thing over at C. And we would then end up with those 2 pictures. So notice the internal forces again continue to be equal and opposite. And if we just take a look at all those free body diagrams, we would see that we've got joint D, joint B, and joint C each have 3 unknowns. Joint A actually has 4 unknowns. Now these are points, right? Those joints are points, so there's only 2 equations of equilibrium at any free body diagram at any point in space. So let's take a closer look to see if there's a good starting place here that we could begin our analysis. Is there a joint that looks more favorable? Although they have 3 unknowns, so we're not going to be able to solve for all of them. Take a look at joint B. Anything look interesting about joint B? And it sure does. If at joint B, if we sum forces in the y direction, we're going to get 0, and that's going to tell us that PBD minus 4 kilonewtons equals 0, giving us PBD is equal to 4 kilonewtons. So we end up with a positive number, so I would say or 4 kilonewtons in tension. All right, so with our work at joint B, solving for PBD, right, we've also solved for PBD on joint D, so I'm going to go down here and I'm just going to redraw joint D for us. So we've already found that that was equal to 4 kilonewtons, and we've got PCD and PAD. And we can keep in mind of our geometry, which would be 2 to 1.5, and same thing on the other side, 1.5 to 2. So nothing that we can get with a single equation, but if we go sum of the forces in the x direction, that would be 3 kilonewtons. We'd have plus PCD in the x direction minus PAD in the x direction. All those have to equal 0. Sum of the forces in the y direction equals 0. We'd have minus 4 kilonewtons minus PAD in the y direction minus CD in the y direction. That has to equal 0. So getting to our numbers down here and just dealing with the geometry, 2, 1.5. And so by the Pythagorean theorem, you would find that hypotenuse was 2.5. So we're going to end up with some simultaneous equations. So I'm going to rewrite sum of the forces in the x direction. That's going to be 3 kilonewtons plus, and so the x component of CD would be 2 over 2.5 of PCD. That's going to be by geometry minus 2 over 2.5 of PAD, and that equals 0. I'm going to do the same thing. It's going to look a little different. We're dealing with the y components, which would be 1.5 over 2.5. So we end up with an equation that looks like minus 4 kilonewtons minus 1.5 over 2.5 PAD minus 1.5 over 2.5 PCD equals 0. So there's our two equations, two unknowns. So we'll go through a quick solution. I'm going to take both equations and I'm going to multiply by 2.5. So what that ends up doing then is canceling 2.5 in the denominator. So I'm just going to go ahead and take that away. And so we've got 2.5 times 3, 2.5 times negative 4. And so what I'm trying to do is get ourselves ready to cancel. And so now I'm going to take this equation, the whole equation, and I'm going to multiply by 1.5. And I'm going to take this one on the bottom and I'm going to multiply it by 2. And then I'm going to add the equations together. And so although it's going to look a little funny here, I'm going to add to that 2 times 2.5 times minus 4 kilonewtons. And I don't quite have these lined up correctly, but there's PCD and PCD. So I'm going to take that 1.5, which is multiplied by 2. That gives me 3. On the second equation, I've got 2 times 1.5 and that negative sign. So when I add them together, PCD cancels all the way out. And so I would have minus 3 PAD, that's the 1.5 times 2, and then minus 2 times 1.5 minus 3 PAD, that equals 0. So then bringing the math all the way home, take the negative 3 and the negative 3, put them to the other side, that gives me plus 6 PAD on the other side. On the front side, we have minus 8.75, so we can divide that, and we would find that PAD is equal to minus 1.46 kilonewtons, or 1.46 kilonewtons, and I'm going to put a big C in compression. So right, I drew PAD initially in tension. So negative would then correspond to compression. All right, so I'm going to take this free body diagram. I'm going to go ahead and copy it. I'm going to paste it right down here. And let's just make sure we're all on the same page. We have just found that PAD is no longer an unknown, but it's going that way, 1.46 kilonewtons. So now this free body has one unknown left in it. And so I'll fish out that equation for you. We could use either one of those equations to go ahead and solve for PCD. So I think I'm going to go ahead and fish it out here. It's going to be from, I'll use the top one, 2.5 times 3 kilonewtons plus 2 times PCD minus 2 times PAD, which is minus 1.46. And that obviously is kilonewtons in there. So you can now solve for PCD. All right, so let's go back to our free body diagrams. We just kind of take a big, going to put a check next to the ones that we have. All right, we just dealt with joint D. Now all of a sudden, joint C looks pretty good. All right, we've got now just two unknowns left, PCD and F3. And so you can see how the dominoes would fall. We would use equilibrium at joint C. We could then use our answer PBD or PBC and some of the forces in the x direction back at joint B, and then we could find PAB. And actually then we would have all the internal forces. So let's take a look at another way, though, that we could have started our problem solving off here. And so let's go back and take a look at this whole structure free body diagram. So this one was externally determinate. There were 3 external unknowns. So we could have used the whole structure free body diagram, solve for F1, F2, and F3, and then done the method of joints or the method of sections, started cutting out free body diagrams. So let's just go over that real quick. So I'm just going to go ahead and copy this free body diagram. And let's go ahead and just put it right underneath where we were just a second ago. So I'm going to draw a couple lines right here. And then let's just go ahead and paste that right there. So we've got that free body diagram, and let's do some equilibrium on it. So we're going to sum moments at point C. That equals 0. I'm going to go clockwise positive. And we're going to be able to solve for F2. And let's just get this in there. F2 times 4 meters minus 4 kilonewtons times 2 meters, that applied load, plus 3 kilonewtons times 1.5 meters. And all of that would equal 0. And so doing the math, we would find that F2 is equal to positive 0.75 kilonewtons. We can sum moments at point A. That equals 0. I'll go clockwise positive. So if I spin a moment over here, that's going to give me the ability to solve for, here I'm just going to solve for the y component of F3. So we would end up with an equation that looks like 3 kilonewtons times 1.5 meters, right, from the load above, plus 4 kilonewtons times 2 meters, minus F3 the y component multiplied by 4 meters. That equals 0. Go ahead and solve that. It says that F3y is going to equal 3.125 kilonewtons. And if we go ahead and take a look at the trig, we would see that F3y over F3 would equal cosine of 30 degrees. So the cosine of 30 would be F3y divided by F3. And so that would tell us that F3 would equal F3y divided by cosine 30 degrees. And so we'd have 3.125 kilonewtons divided by cosine 30 degrees, and that's going to give us 3.61 kilonewtons for the vector F3. We're going to need the x component here in just a second, so F3x would equal F3 times sine 30 degrees. That would be 1.8 kilonewtons. And so the reason I wanted that was because some of the forces x has to equal 0. So we would have F1 plus 3 kilonewtons minus 1.8 kilonewtons, right? The x component of F3. And that would give us that F1 was equal to minus 1.2 kilonewtons, or 1.2 kilonewtons to the left. Always remember that that negative sign right there relates to the picture that we got it from, and nothing else. It doesn't relate to any sign convention. It relates to the picture of the free body diagram. And so you get a feel for, this way we now have a whole structure free body diagram that has 3 kilonewtons, and we've solved for 1.2 kilonewtons F1. F2 was 0.875 kilonewtons. That's still the applied load, 4 kilonewtons. And we would have 1.8 kilonewtons and 3.125 kilonewtons. So there would be our solved free body diagram. And now we could go about looking at all of the joints again. So the major thing that has not changed, right? Up at joint D, we still have the exact same free body diagram we've had before. Same with joint B. But over at A and C, right, those free body diagrams would actually look quite a bit different. So let's just go ahead and draw those really quick. 1.2 kilonewtons, 0.875 kilonewtons, and PAB, PAD. So you could see now where that would be an attractive first joint, because we have those external supports. We have the external forces already solved for. 1.8 kilonewtons, 3.125 kilonewtons. And then the internal forces, PBC and PCD. So that also would be a attractive first joint now to deal with, when neither of those were very attractive when we had not obviously solved for the red arrows to begin with. And so the very last thing is, let's just take one quick look. Let's take one quick look at a section cut. And so we were just cutting out joints, but we could perhaps have cut all the way through right there. And so let's take a look at the section that results. So we go ahead and drop that side. And so we would see here that would be PAB. I'm going to draw it in tension PBD and PCD. So that's a pretty good looking free body diagram as well, and we would have lots of options, but the reason why it's so good is because we have 3 unknowns on it. We could solve for those 3 internal forces. So solving for the external supports in this case gave us more options, but if you remember from above, we were able to do the problem also without solving for them. So neither one would be more right or wrong than the other.